So I just wanted to say a little word about neuroscience. I don't have time to talk about this too much, but my PhD was in neuroscience, my undergrad was in computer science, and we try and combine both those two areas at DeepMind. So we're very interested in systems neuroscience, and we're quite interested in systems level. So that means the algorithms and the representations and the architectures the brain uses, rather than the specific implementation details of synapses and cortical columns. So it's the kind of higher computational level that we're very interested in. And the reason we're interested in systems neuroscience is that we think it's very important to look at the brain as a source of inspiration for new algorithms, but probably how those algorithms are going to be implemented in a computer relative to the brain will be different, because of course silicon is different from wetware carbon. So we don't think that actually exactly copying the specifics of the implementation details is the right way to go if you're interested in building AI. So the kinds of things we're using neuroscience-inspired ideas for is memory, attention, concepts, so kind of abstract knowledge, planning, navigation, and imagination. All these different areas that we would like to imbue our computer systems with the ability to do. And in fact, one of the brain areas called the hippocampus, that's here in pink in the center of your brain, this is what I studied for my PhD, turns out to be quite critical for a lot of these functions, for memory, for navigation, for concepts, and for imagination. So actually, and the hippocampus, obviously the neuroscientists here will know, but those of you aren't, the hippocampus is quite a different structure from the cortex. It's 3-layered instead of 6-layered. It's a much more ancient structure. All mammals have hippocampuses. And it's very interesting to think about what functions the hippocampus actually provides for the whole brain. So you can think of one of the projects we have going on at DeepMind is to create a kind of artificial hippocampus. So now I'm going to talk about, of course, Alphago, which is obviously now very right in the news. The reason we chose to work on Alphago, which I'll explain in a little bit, is that we wanted to see if these kinds of deep reinforcement learning techniques, deep learning and reinforcement learning, could be put together with planning. Long-term planning. And Go is actually the perfect testing ground to do that, because obviously it's a very intuitive game, and but you have to do calculation and planning as well. So I'll assume pretty much, because I'm in Korea, all of you know how to play Go, so I'm not going to explain that. But obviously here's the Go board. Of course, as I've talked about many times and I'm sure you've seen me talk about this in press conferences the last couple of days, it has a hugely rich tradition and history with 40 million players today and 2,000 professionals. It's probably one of the most studied games that humans have ever studied, which is fantastic. So that means that the level of challenge is very great. And obviously, just one figure showing how complicated Go is that the number of possible board configurations is 10 to the power 170, which is more than the atoms in the universe. And I've been told that the number of possible games that you can play is 10 to the power 700. So these immense numbers. So why Go? Why did we decide to take on this challenge a couple of years ago? Well, as I said, probably the most complex game that mankind has ever devised. Certainly that's played professionally and is a perfect information game. It's been an outstanding grand challenge for AI for several decades, especially since Deep Blue beat Kasparov. So there have been many projects and efforts on trying to crack the game of Go. Of course, we were very attracted to this because any solution and playing this game, humans require intuition and calculation. So any solution we would come up with would involve combining pattern recognition with planning. So for us, that was the next stage after the Atari games. So why is Go so hard for computers to play? Well, this immense complexity, this 10 to the power 170, makes brute force search techniques intractable. So you can't just search out everything. And there are two main challenges really to writing a good Go program. One is reducing this huge search space to something manageable. And the second thing is that it was thought to be impossible to write an evaluation function to determine, to tell the machine which side is winning in a particular position. And actually, having been here last couple of days, watching the 9Dan professionals commentate on the game, and like yesterday's game was obviously very exciting, and I'm going to talk about that in a little bit. Actually, a lot of the 9Dan professionals were divided in their opinion about who was winning through most of the game. And I didn't realize that even at that level, for a close game that's very complicated, evaluating who is winning is very tough. And what was interesting is that Alphago was pretty confident, even though we as the team were very nervous, that it was winning from, it was doing better from around halfway through the game and increasingly more and more confident. And it's interesting to hear Lee Sedol in the press interview afterwards saying that he also felt that he was behind in the game for most of the game and couldn't catch up, which is also what Alphago thought, but not what all the other 9Dan professionals who were commentating thought. So this is very interesting. So how did we, so let me just illustrate the complexity of this compared to the next most complicated perfect information game, chess. So in chess, which is the one I know well, in an average position, there are maybe around an average of 20 possible moves. So the branching factor in chess is around 20. In Go, by contrast, in an average position, there's more like 200 moves. So the branching factor is one order of magnitude bigger. So also Go games last for much longer. They're much longer games. So the complexity of the search tree is just really huge. Secondly, there's this issue of intuition again versus calculation. So I play Go. I'm not very strong, but I play it well enough to understand and appreciate its beauty. And, Go is primarily a game about intuition rather than brute calculation. So even when you ask some very strong players, why did they make this move? They will tell you often that it just felt right. And so their subconscious intuition was telling them this is right. So in effect, what they're using is all of their lifelong learning and experience to bring to bear on it. But they haven't consciously calculated it out in a logical sense in the way, say, a chess player would tell you. They'd be able to tell you exactly why they made the move and the reasons, the calculations they made. Of course, Go also requires calculation, but I think what separates the weaker players from the stronger players is their intuitive ability. And probably the reason for this, and I had dinner with Lee Sedol before the matches started, and we had a great discussion about games playing and games playing ability, and he confirmed to me that this was the case about intuition, and I think he's a great example of a fantastically talented intuitive player, the best in the world. And he agreed that because there's so many possibilities in the game of Go, that's why even top players have to rely on their intuition, because the myriad of possibilities is just too large. The other really difficult thing about writing an evaluation function compared to chess is that in Go, there's no concept of materiality, right? So in chess, the queen is worth 9 points, the rook is 5, the knight is 3. So as a first approximation, you can just add up the points on each side and roughly tell who's winning. Of course, you need to do a lot more than that to make a really strong chess program, but that will already get you started. In Go, this is impossible because obviously all of the pieces are worth the same, and it's very unclear in the middle game whose territory is whose. So how do we overcome these two challenges? Well, we turn to deep neural networks and deep learning. So we actually built two neural networks. So the first one, we started off with about 100,000 games that we downloaded from the internet, Go servers, and of human expert data. But it was a mixture of kind of strong amateur, it was probably like strong amateur level games. And what we used, we trained our first neural network, which we call the policy network, and we trained it in a supervised learning fashion. And what we trained it to do was we took positions out of these games, and obviously we knew what the human expert player did, which move they played next. And we trained this policy network to predict and mimic what the human player did in that position. Then once that got reasonably good, we got the supervised learning policy network to play itself many thousands, even millions of times. And we use reinforcement learning now to, instead of just mimic the human experts, actually what we wanted to do was play better than the human experts, certainly the amateur level players. And so what we did was we optimized during this self-play for win rate. Ultimately, which is actually ultimately what you want a computer program to do. You're not interested in mimicking the right moves. You actually want it to increase its winning rate. And so this sort of refinement of the policy network with reinforcement learning created a new policy network that could beat the original one 80% of the time. So it's a lot stronger. Then we froze that network and we got that to play itself 30 million more times. And that generated our final data set, which we called our gold data set, of 30 million positions, one position from each game. And of course, now we had this database of more games than probably ever been played, and we were able to now try and attempt to create this fabled evaluation function. And what we did is we had 30 million positions, and we also knew the end results of those games. So we used that as the training set to train this new neural network, the value network, here in pink, to actually make a prediction about who was winning, who was going to ultimately win from any position. So after all of that training, we end up with two neural networks. The policy network here in green that takes a board position as an input, and the output is a probability distribution over the likelihood of the moves from that position. So the green board that you can see here on the top, the size of the green bars is the probability that Alphago assigns to the likelihood of that particular move at that particular board position. So the higher the green bar, the more probable. And the second network we get is the value network, which also takes a board position in as an input. And then the output here is a single number between 0 and 1, a real number, and 0 indicating white is winning completely, 1 would be indicating black is winning completely, and 0.5 would mean even game. And this is the key to the power of the strength of AlphaGo. So now we have those two neural networks. We can combine that with Monte Carlo tree search and also a rollout policy to create the final AlphaGo system. So I'm just going to explain very quickly with this diagram how that works. So let's imagine that AlphaGo is thinking about making a move. So imagine it's in that top board position represented by the node there, the small little Go board. And it's done, maybe we're halfway through the search, and it's done a bit of searching. And you can see here that so the Q value is the estimated value of that particular move from that position. And we want to follow down the most promising path, so where the Q values are highest. And you can see that the AlphaGo will follow the tree down to a position where it's never considered it so far in this particular from this particular position. So you can see that here's the left-hand arrow at the bottom, the black arrow. Now it now has to create a new part of the tree. So it calls the policy network to expand the tree at this point. So the green network I was describing, and but we don't add in all the possible moves that are from that position. We only add in the top 3 or 4 most probable moves that the policy network is saying are most likely. So that really cuts down the size of the search tree. So we expand the search tree at this node in that fashion. Then once we've expanded the search tree, we now call the second neural network, the value network, to evaluate that new position in the tree, that new node. We also combine it with a second way of evaluating the position, the more traditional way, which is called the rollout policy, which is actually to roll out games all the way to the end of the game and then collect statistics of how many wins and losses there were for each side. So it's kind of 2 different ways of evaluating the position. The value net, which instantaneously evaluates the position, and then the rollout policy that does a kind of statistical analysis of the position. And actually, we found AlphaGo is stronger if you combine those 2 different evaluations together. And we mix that together to give a final evaluation. And once we've done that, we then back up these new Q values, these new evaluations, back up the tree. And then when AlphaGo has run out of time and it needs to make a move, then it basically picks the move that has the most promising Q value associated with it. So let me just explain now with this diagram how that helps with this combinatorial problem that Go has. So imagine that this is the search tree from a position in a Go game. Obviously, it's just it's this huge search tree of possibilities, and what you can think of is that the policy network actually cuts down the breadth of the search. So instead of searching all these 200 moves from each position, we just search the top 3 or 4. And then you can think of the value network as reducing the depth of the search. So instead of having to search all the way to the end of the game to find out who won and doing that millions of times, at any stage we can truncate the search and call the value network to get an estimate of how well AlphaGo is doing in that situation. So now you can see with these two neural networks, we've completely reduced the search space down to something much more tractable. So how did we evaluate AlphaGo once we built it? Well, sort of last summer, actually last spring, we started evaluating it against the other top programs that are available. And actually the best programs, commercial programs, are called Crazy Stone and Zen. And they're both around 5 Dan, 6 Dan amateur level. And when we ran AlphaGo against these programs, AlphaGo won 494 out of 495 games. And in fact, it has a 75% winning rate against Crazy Stone and Zen, even if it gives them a 4-stone handicap, which is pretty huge. And obviously, AlphaGo is even stronger on distributed machine. So the gap between AlphaGo and the next best programs is more than 1,000 ELO points. Actually, this is a lot larger now because this is the AlphaGo version from October that I'm talking about here. So then, as you'll all know, we beat all the other programs very convincingly. So now it was time to test against professional human players. So we called up our esteemed opponent, who has now become a friend of ours since the match, Fan Hui, who is the European champion of the last 3 years. And he's written books about Go, and he coaches the French national team. He grew up in China and became professional there, and he's 2-Dan pro. And in October, we played Fan Hui in a match, and we won, surprisingly to us, 5-0. So AlphaGo became the first program ever to beat a professional player in an even game under tournament conditions. And this was very surprising to the machine learning and AI world, and I think the Go world. It was more than a decade earlier than many experts, even expert programmers from programming other Go programs, were expecting. So again, this was a front cover Nature paper a couple of months ago. So if you're interested in the details of how it all works, it's all detailed out there in the paper. And it created quite a big stir in the academic circles in terms of downloads and other things. So now, as you all know, we're here. It's the final, kind of ultimate challenge. I think, playing Lisa Doll, and in this 5-game match. Now, of course, we're currently 2-0 up, but the games have been very close, very interesting, and I think anything can happen still. That was my prediction before we came in it. We knew that AlphaGo was quite strong because in our internal tests, we test the programs against older versions of itself. So the new version of AlphaGo has played, hundreds and thousands of games against many different older versions of AlphaGo. And because of that, we can estimate how strong the new one is, because we know how strong the October one was, because we calibrated that against Fan Hui. right? And we know how much better Lee Sedol is than Fan Hui, and we know how much better our current program is better than October. So we can be quite confident about the intersection of that. But the problem is, reason there's high uncertainty for us is that obviously there can be some problem of overfitting because there are all different versions of AlphaGo. So we try and keep diversity in the tournament pool. But ultimately, they're still based off of the same kind of techniques, even though they have different hyperparameter settings and other things. We also try to, for example, make sure that our old versions are kept in the pool and they're given high handicaps. So it's sort of many challenges for the new version of AlphaGo. So we can't be sure until we play these matches that there wasn't some whole area or some type of position that for some reason AlphaGo never gets into when it plays itself. And newer versions can beat the older versions, but they're still not experiencing this particular type of position. So we don't think there are any holes like that, but that's why we wanted to play someone as amazing as Lee Sedol, who is famed for his creativity and fighting style. And so if anyone can find the weaknesses, it will be him. And we wanted to know if there was some big weaknesses that we didn't know about. Because, of course, we can't evaluate it anymore. It's way too strong. It's been way too strong for us for more than a year. In fact, we have one strong Go player on our team, Aja Huang, who is 6-dan amateur, but it was able to beat him from, more than about a year ago. So we have no real way of evaluating with this ourselves. I've spent many nights looking through AlphaGo games against AlphaGo, and it looks amazing to me. But some unbelievably beautiful games. But I'm not an expert player, so I can't say for sure. So it's been a real honor and privilege to be able to play Lee Sedol and get to know him, and I wish him the best of luck in the next 3 games. No, I mean that. So. And so I want to just mention about compute power that we're using, because I think I got quite a lot of questions on the internet about this. We're actually using roughly the same compute power as we used for the Fan Hui match. So it isn't some crazy amount of compute power. It's about the equivalent of sort of 50 GPUs, 100 GPUs, that kind of level. But I want to just say that the reason that we're not using more computer power is because you actually get a lot of diminishing returns with compute power, because it's, for example, very hard to parallelize Monte Carlo tree search. It's known to be very hard to parallelize. So you get really diminishing returns for each extra, GPUs you add. So, and actually we drew those graphs. If you look in the supplementary materials of our Nature paper, you'll see that we drew the performance curves of adding more GPUs, how much does it improve? And actually you basically asymptote. So it really is an algorithmic advance, not a hardware issue. And just probably quite surprising to most people, which is why I want to say it more clearly, is that the distributed version of AlphaGo is only 70% win rate against the single machine version of AlphaGo, right? So it's only about 200 ELO point difference. So it's really, it's maybe 1 or 2 Dan rankings weaker. So it's not that, it's still very, very strong. Of course, for a match like this, we want to use the strongest version we have, which is the distributed version. But the single machine version is also incredibly strong. So how does AlphaGo differ from Deep Blue? Well, I talked about Deep Blue at the beginning and the immense achievement that was. But AlphaGo really, for us, we're very pleased with the performance of AlphaGo, and we're very proud of how it's worked, and I'm super proud of the team, amazing team that built it. But for us, it's not so important just the achievement of winning against the top professional. It's also actually more important to us is how we did it, what the methods that we used. And here's the sort of differences. Deep Blue used handcrafted chess knowledge distilled by the programmers from talking to chess grandmasters. AlphaGo, by contrast, is knowledge learned from expert games and self-play. Deep Blue used full-width search AlphaGo obviously uses the neural networks to do very selective, highly selective search. And you can see that in this quite surprising figure, I think, is that even though AlphaGo is, we're 20 years on from Deep Blue, so obviously machines have got a lot faster, but Deep Blue was analyzing and looking at 200 million positions per second, whereas AlphaGo only looks at 100,000 positions per second, much, much less. So, and that's because it's more human-like in the way that it tries to play. So of course, human players, top players, search much, much less than this as well, maybe, a few hundred moves. But they use their enormous knowledge and kind of experience, which is coded in the neural networks of their minds, to actually do good judgment and intuition about what moves are worth looking at and what kinds of positions are good. And AlphaGo is, whilst definitely not as efficient as a human, is more towards that end of the spectrum. So I'm just going to end now by talking about a few bigger picture things. And of course, playing games is extremely fun. It's great for development of the algorithms, and it's very exciting, amazingly exciting when we have matches like this. But the motivation for us at DeepMind is not just to play games, of course. We want to use these techniques we've developed and apply them to all kinds of important real-world problems. So the things we're looking at are healthcare applications, robotics and control of robots, and smartphone assistants, making them more intelligent and smart on your mobile phone. And we hope that we're going to start working on these things soon, and we hope that the technologies and the methods we've been developing for AlphaGo, when we extend them in the future, they'll be used in all these kinds of areas. So let me just talk about the philosophical level of why I've worked on AI for more than 20 years, and I believe it's one of the most important problems we can work on. I think that two of the big issues facing us as a society today are information overload. We're just deluged with data, both as users and as scientists, all the way from important things like genomics and physics, so much data, to things like entertainment, where there are more TV channels than we can comprehend. So all these things mean that they have too much information for us to process. Then there's also system complexity. So the kind of systems we would like to understand better and master as a society are incredibly complex themselves. So climate, disease, energy, macroeconomics, all of these things are incredibly complicated systems. And so I think of AI as a kind of meta solution to all these other problems. If we can make AI work in this kind of general way, then we should be able to apply it to help human scientists and clinicians and researchers to advance their areas more quickly. So for me, the dream is to use this kind of AI we're developing to make AI scientists or AI-assisted science possible. And just a quick word about ethics and responsibility. As with all powerful new technologies, and AI is no exception, they must be used ethically and responsibly. I think that technology is kind of neutral in of itself, but it depends on how society decides to use it, whether it determines whether it becomes for good or for bad. And I think human-level AI, general AI, is decades away, but we should start the debate now and research into these ideas and think about how we want to deploy these kinds of technologies. And then finally, as a neuroscientist, I'm also very intrigued by our own minds and how they work. And I actually think that trying to build AI in this neuroscience-inspired way, in this general way, and then comparing it to the human mind will maybe allow us to better understand some of the mysteries of our own minds. Things like what the nature of what dreaming is, what the nature of creativity is, and perhaps even start getting towards be able to answer the question of what is consciousness. So I just want to end by thanking my amazing AlphaGo team, all the people responsible for that. And then to also mention that we're, of course, hiring. And if you want to work on these kinds of things, please feel free to apply. Thanks.